Hi everyone. In this video we are going to cover section 3.5, derivatives of trigonometric functions. So this is for the first time that we're seeing a little bit of trigonometry mixed in with calculus. And we're going to get derivatives for all 6 trig functions. We'll spend a little bit of time talking about sine specifically to start with. Now our text, OpenStax, it goes through a couple of different explanations as to why the derivative of sine is what it is. Some of them are pretty technical. I'm not going to expect you to show any of them. I'm going to go through a much more visual reason why the derivative of sine is what it is, and I'll start it out like this. We're going to basically plot the derivatives, the slopes of the tangent lines at various points on the same grid, and then maybe you, or you'll just listen to me tell you, but maybe you'll recognize what that derivative looks like. All right, and I'm going to start right here at pi over 2. The slope right there at 90 degrees or pi over 2 radians, the slope is horizontal. There's a horizontal tangent line there, and the slope is 0. So I'm plotting the slope at that point. Okay, hey, I can plot some other 0 slopes. There's that horizontal tangent line right there. I've got another horizontal tangent line right there at negative 3 pi over 2, and also at positive 3 pi over 2, I see another horizontal tangent line. All right, cool. So that's a good start. So we have 4 points to our derivative graph. Now, I'm going to look at this point right here at 0 degrees or 0 radians right there. What does the slope look like there? Well, if I look at my grid here, I don't have a perfect, counting by ones grid, but that slope appears to be at roughly a 45-degree angle at that point, and it actually is. The slope there is at 1. And so I'm going to plot that 1 for my derivative graph, which is about there. Okay, continuing on let's get some more points on our derivative graph. Here we have over at pi radians, now the slope appears to be negative, and it is actually, in fact, negative 1. So I'm going to plot that point. I can plot another slope of negative 1 right about there. And I think I have enough points to graph this curve. I'm just going to play connect the dots and draw a smooth curve through these points that I have here, coming up past 0, up to positive 1, back to 0, whoops, there we go, back to 0, negative 1, and then back to 0 again. Okay, and so if you want, you can pause the video, think really, really hard in your brain. Now we're talking trig, but what is that the graph of that starts at 0 degrees or radians up at positive 1, and then decreases down to negative 1 and then back, and has a nice little periodic style, just, similar to sine. And if you did pause the video, maybe you came up with it. This derivative here, f prime of x, is equal to the cosine of x. That's right, the derivative of the sine curve is the cosine curve. The slope at any point on the sine curve is the cosine at that exact same point. Okay, so that's kind of a really cool relationship that those two functions have together. And like I said a few minutes ago, the text does have derivations of why this is in fact true. They go through with the limit definition of the derivative. I'm not going to do that in this video, but you can feel free to read through it on OpenStax if you choose to. But what you really need to remember, you really got to have in your brain, is that the derivative of sine is cosine, and then when we differentiate the cosine of x, that is negative sine x, and that's just because basically it flips over if you're looking at the slope of points on the cosine curve. All right, it's the same as the sine curve, but it's negated. Okay, and you could do that same visual and show how well that works out. Okay, so derivative of sine is cosine, and the derivative of cosine is negative sine x. All right, now let's use that in a couple of examples. And we're not just differentiating the sine of x and the cosine of x, but we have these functions that have lots of, that have other things going on. And in this first one, checkpoint 325, we can see here we have the sine of x and the cosine of x, and that is a product. Right, there's a times there that's implied. So for this one, we have to use the product rule. Okay, so it's important to analyze the problem, look at it, and figure out what you need to do to take that derivative. We don't just differentiate sine and cosine individually. You would if there was a plus sign between them, but not when there's a multiplication sign. All right, so f prime of x is equal to, I'm going to take the derivative of this guy first, the sine of x. Derivative of sine is cosine x times cosine x plus, now I'm going to take the derivative of that guy, and I'm going to throw it into parentheses because I've got an extra negative sign coming in. Negative sine x times the sine of x. All right, so f and g, right, from the earlier section on product rule, f prime g plus g prime f. All right, now let's simplify that. F prime of x is equal to cosine times cosine. We write that as cosine squared x. And just as a side note here, this is a little star, and when I write that cosine squared x, that means the exact same thing as parentheses cosine x squared. Those two things are synonymous. They mean the exact same thing. It's just we like to not write as much in math if we don't have to, okay? And we can eliminate the parentheses by pulling the squared in and writing it over the cosine, okay? And that is very different, not the same as when we write the cosine of x squared. In the bottom one, what I wrote down is my x is squared. In the top two, the whole function is squared, all right? Back into the problem now, plus a negative, so I'm going to write that as minus. Sine times sine is sine squared x. Now, I know my trig identity super well. If you don't, that's okay, but I know that that simplifies to f prime of x is equal to the cosine of 2x. Not squared, the cosine of 2x. That is a double angle identity. Again, if you don't know them perfectly well, that's fine. There will be times during the course that we will use various trig identities, and I'll always make a point to let you know when that's happening. Moving on to the second example, and take a look at it, analyze it. What are we going to need to do in this one? We use the product rule. Again, I have an f, a first function, and a g, a second function. So when I take my derivative, f prime of x, the derivative of the first part is 15x to the second times the sine of x, f prime g, plus g prime cosine x. I don't want to write that first. I'm going to write my 5x cubed first, and then times the cosine of x. Okay, that's basically it for that one. I could probably factor, so I would accept this as a correct answer. It would not be wrong, though, to say, all right, I have a 5 in common to both terms and an x squared in both terms. So I'm going to pull that out in front, and that leaves me with 3 sine x plus x cosine x. All right, I'm good with you writing your answer either way for that one. Let's do one more here before we move on with a little quotient rule action. Now we have a numerator and a denominator, so I'm going to call my numerator f, and my denominator is g. And there, hopefully they just popped on there. There we go. All right, so when I take my derivative, g prime of x, differentiate the numerator first, negative sine x. The derivative of cosine x is negative sine x times 4x squared minus, because it's the quotient rule, derivative of 4x squared is 8x times the cosine of x. All that gets divided by 4x squared, and that is to the second power. Ooh, that looks a little bit messy. So we'll clean this up a bit. This is equal to, I'll start with my denominator. 4 squared is 16, x to the fourth. And then let's write our numerator as negative 4x squared sine x minus 8x cosine x. And in this one, I am going to factor because I can see that I'm going to have some cancellation. All right, and you'll see what I mean in a second. Let's take out a 4x from both terms. Negative x sine x minus 2 cosine x divided by 16x to the fourth, and that 4x in the numerator cancels a little bit of stuff out of the denominator. So I'm going to rewrite what I have left, g prime of x, negative x sine x minus 2 cosine x divided by 4x to the third power. So when you're using the quotient rule, always check and see if there's any factoring that you can do to simplify that fraction. Okay, so now we're going to go into and find the derivative of our tangent function. And what's cool with this, and we can do this with all of the remaining trig functions, is we can differentiate them just by knowing the sine and cosine relationships. And I'll show you what I mean. All right, I want to take the derivative, so I'm going to write this one a little bit differently. The derivative with respect of the tangent of x. Well, I know that tangent is the sine of x divided by the cosine of x. So now I'm taking the derivative of this fraction. Hey, I know how to take the derivative of a fraction, quotient rule. Hey, I know the derivatives of sine and cosine, so we can do this without me saying, before we even are told, this is the derivative of tangent. This is showing where it comes from. Okay, so I'm going to take the derivative of the numerator first, cosine x, times the denominator, cosine x, minus the derivative of the denominator, negative sine x, times positive sine x. All that is divided by the denominator squared, cosine squared x. Cool, so that's our derivative. Now let's clean it up, see what happens. Up in the numerator, cosine times cosine, let's write this down here, is cosine squared x, minus negative is plus, sine times sine is sine squared x, over cosine squared x. It would be incorrect to cross out those cosines, right? Because the one in the numerator is in a sum, so you can't just pull that off and cancel out. But who knows their trig identities? Numerator, what's that numerator equal to? I'm not actually waiting for you to answer. I'm just pausing to give you wait time to think about that, right? What's that numerator equal to? Pythagorean identity says that that is 1. 1 divided by cosine squared x. And I can even write that much cleaner, much neater. That is equal to the secant squared of x. All right? So when my function is tan x, its derivative f prime of x is equal to secant squared x. And like I said, we could do that for all 5 remaining trig functions. Cotangent would be flipped over, but the work would be virtually identical. I could do secant and cosecant by writing them as their reciprocal function, 1 over cosine, 1 over sine, respectively, and all of them just using a quotient rule and simplifying. I'm not going to go through all of them in this video, but you could challenge yourself, or maybe it'll be on the homework, to write out some of them and use the quotient rule to see where they come from. And here we have the remaining 4 summarized. The derivative of tangent is secant squared, as I just showed you. The derivative of cotangent is negative cosecant squared. The derivative of secant is secant x tangent x. And the derivative of cosecant is negative cosecant x cotangent x. Okay, so these are a little bit involved if you had to memorize them, but you're just going to need to use these derivatives in problems. One thing to remember, if it starts with a c, its derivative is negative, same as the derivative of cosine is negative sine. If it doesn't start with a c, its derivative is positive. That's just something to help you remember a little bit. All right, so let's use some of those in an example. Cotangent specifically, and in this example we're going to write an equation of a tangent line to our graph of cotangent x at x equals pi over 4. Okay, so tangent line, I need a slope at a point, and then we use our point slope formula. So I'm going to write f of x equals the cotangent of x, its derivative f prime of x is, if you need to look back in your notes, flip back a few seconds in the video, negative cosecant squared x. All right, there's our derivative. And then what do we do now? We're going to say I need the derivative at the point pi over 4. All right, I don't know the cosecant of pi over 4 off the top of my head, but if I'm evaluating this and I'm maybe using my calculator, I can write that as 1 over sine squared, maybe let's write this in parentheses, 1 over the sine of pi over 4 squared. Okay, so this is, different people have different comfort levels with their calculator. If I really need to evaluate this trig function at pi over 4, I want to do it in a way that I've done before. So cosecant, a little bit more complicated, confusing to work with, but I can write its reciprocal function and then evaluate that in more standard ways. Maybe I know the sine of pi over 4 off the top of my head, but I could certainly use my calculator to assist. I'm going to see if I can bust this out without a calculator. Let's see. So I have 1 over, in parentheses, the sine of pi over 4, radical 2 over 2. I'm squaring that. Negative 1 over, regular 2 over 4. That flips over. 4 over 2, negative sign still in front of it, 2. Check that in your calculator. See if I got it right. I hope I did, or else I'm going to look really bad in front of all of you. And what is that 2 that we just found? That is our slope. That's the slope at the point pi over 4. Oh, and just kidding. It's actually negative, right? I lost my negative sign. I carried it all the way through the problem. Here it is here. Here it is there. And then I lost it for a second. But I found it. Then that 2 is negative. So we have a slope of negative 2. Now, last part of this problem, we're going to say, all right, what's my point slope formula? Y minus y1 equals m times x minus x1. And substitute in everything. Y minus our y coordinate at pi over 4 is 1. I didn't find that yet. I'll show you in a second where that comes from. Equals negative 2 times x minus the x coordinate, pi over 4. Okay? If you didn't know where that 1 came from, my function is cotangent. If I take f of pi over 4, the cotangent of pi over 4 is equal to 1. And the reason for that is the tangent of pi over 4 is 1. So flip that over for cotangent, and you also get 1. All right? Now, to finish off our problem, we want to write this line in a more simple form. Y minus 1, negative 2x, plus, if you double pi over 4, you get pi over 2. And then the negatives, negative times a negative is a positive. Final answer, y equals negative 2x plus 1 plus half a pi. And I could write that as like one condensed fraction, but I think we'll leave it like that. That's the equation of the tangent line to our cotangent graph at the point pi over 4. And then we close out with higher order derivatives for our sine curve. You could do this with cosine also. We want to find the first 4 derivatives of y equals sine x. Okay, here's what it looks like. Y prime, first derivative, cosine x. Y double prime, second derivative, derivative of cosine, negative sine x. Y triple prime, third derivative, the derivative of sine is cosine, so the derivative of negative sine x is negative cosine x. And then maybe you see where this is going. The fourth derivative, I use a number now, but in parentheses. The fourth derivative, the derivative of cosine is negative sine, so the derivative of negative cosine is positive sine. So the fourth derivative is sine x, and we close our loop. If the original function is y equals sine x, in 4 derivatives, I get back to sine x. And what the significance of that is, let's say that some crazy person wants to find the 65th derivative of sine x. All they would need to do is know what the remainder is when you divide by 4. And if you check in your calculators, 65 divided by 4 leaves you with a remainder of 1. It's 16 1/4. So that means that the 65th derivative is the same as the first derivative because it repeats every 4. So this would be cosine x. And we'll close the video on that. Thank you very much for listening. Get started on the homework. Let me know if you run into any problems. Have a wonderful day.